The textbook calls this compound angle formulas.
Like so?
Formulas?
Right.
And I'm not opposed to that idea. We'll call that PQ.
Call it PQ.
Okay? But a better thing to call these
one last thing, we're
are
going
in
to
fact
join up
not expressions
B.
or equations, but
B.
identities. Okay? So what I'm going to show you is a bunch of things that are not just equal to each other sometimes.
So what we're gonna try and do
sine of
here
this is
is
equal to
find
sine
some
and cos of
angles
this.
and some sides,
Sometimes, for
And what
some
we're
values of
looking
x or
for
some
is a
values of
simple
theta.
way
I'm going to show you ones that are equal all the time for all values of whatever angles you put in.
Because
right?
this has
So
we have a name for them.
wrong
They're
answer.
called identities.
Okay.
Right? So I think that's the
when
best
you
way
do
to
something
describe
like,
it.
okay, you know. Now what we're going to do is you're going to learn 6 of these identities today. Okay, so we've learned a whole bunch of identities today, and this sort of pool is gradually expanding. Right? Now to do the 6, what I'm going to do is I'm going to prove 1 by geometry. So you're going to have to draw a triangle with me.
We'll
draw it like
distributed
this.
to the 10 and to the 8.
Make it fairly large. Make it fairly large. Once we prove the first one by geometry, the other 5 will follow using the other identities we already know. Okay, so there's just one that's critical, and the rest sort of
superficial
flow on
look at
from
this
there.
would be, oh, okay, you're doing sine of both of these.
It does have to be a
One
right
is
angle
sine of
triangle.
one and sine
Does
of
have
the
to,
other.
sorry, I hope that was right angled enough. You see. There's a right angle here in the corner. I asked you to get your calculators out, right? So just quickly evaluate that. Sine 10. And then you're going to add in within this triangle
and sine
another
20.
triangle, such that. Let's put some labels.
Can I
on
get a
this
couple of
thing.
decimal
I think I've
places?
got one of my corners.
Actually, let's get 3. Let's get 3.
0 point.
516.
So what we're going to do is we're going to put in a line that is perpendicular to AB inside the triangle.
We know, in fact,
Perpendicular to
sine 10
AB
plus 20
inside the triangle.
it's sine 30,
like which is a half. Right?
like so.
Oh, look, I'm
Right?
kind of in the right ballpark, but
We'll call that PQ.
it's not the
Call it
same.
PQ. Sine 10 plus 20.
And then one
It's
last
not
thing, we're
equal
going to
to
join up
sine 10 plus sine
BQ.
20.
Right?
So
B,
if
which
it's
is up
not,
here in
and
the
I
top.
have other angles here, right? How do I actually get these to interact and get something meaningful out of it? Okay. Now, by the way, just before
So
I
what
launch
we're going to
into
try and do here is we're going to
These are the
define
kinds
some
of places
angles
we'll
and some
start.
sides, right?
Okay.
And what we're
Actually,
looking
we'll
for
do
is
one
a
of
simple
these.
way
For instance, I
to
might
express
say
this.
sine of
Now, I'm
75,
putting it right up here
break
at
up
the
into
start.
2 pieces which I know exact values
Right?
for. Namely,
Because this has an obvious wrong
45
answer.
and 30.
Okay?
Okay.
When
then I
you
can
do
get
something
some
like,
stuff out of
okay,
this
you know,
using these identities
5
I'm about to
times
show you.
10
But that's not the
plus
main
20.
point.
Okay?
The main
Or
place
maybe
where this is going
10
is calculus.
plus 8.
You're like, what?
Okay.
We haven't
know
even,
how this
we haven't
works.
looked
This
at
is
that.
just
We
the
haven't touched it.
well,
We
the
haven't
proper
read
name
it
for
at
this
all.
is the
We're getting
distributive
there.
law.
We're trying to build the
Distributive,
pieces,
right?
because this
We're
5
We're going to climb a very
kind of gets distributed to the 10 and to the 8. So you get 50 plus 5a. Okay. Now, if we were to do the same thing with trig, right? You might say, okay, what about sine of two different angles? Okay. Now, a superficial look at this would be, oh, okay, well, you're doing sine of both of these. So why not do sine of one and sine of the other? Right? So you might compare it to sine 10 degrees. It's still and sine 20 degrees, which I'd just like you to. I asked you to get your calculators out, right? So just quickly evaluate that. Sine 10.
We made for y.
Don't forget to close your bracket.
And sine 20.
Is an argument that comes from the graph.
Can I get a couple of decimal
Because
places?
tan is periodic every 100.
Actually, let's get 3. Let's get 3. 0 point.
516. So that's why that's
516. 3 dp.
Okay.
So
what you've come up with,
Which is troubling.
right?
Which is troubling because we know in fact what sine 10 plus 20 is. It's sine 30,
In fact, it almost never.
which is a half.
Right. So we're going to
So
use
it's like,
this
oh,
triangle.
look, I'm kind of in the right ballpark, but it's not the same.
For what this is equal
Sine
to, okay?
10 plus
But,
20
I like this one
is
because
not
it's
equal
simple.
to sine 10.
I called this A and I
plus
called
sine
that
20.
B because I'm
So
going to put
if it's not,
and I have other angles here.
alpha with
How do I actually get these to interact and get something meaningful out of it? Okay. Now, by the way, just before I launch into this, right?
Yes, good.
These are the kinds of places we will start.
Now,
Okay.
I've got alpha
actually,
here,
we'll do ones with
beta
exact
here.
values.
I
So,
need
for
one
instance, I
length,
might say
because I can do
sine of
everything I'm about to
75,
do,
which I can
without
break
knowing
up
what
into
its
2
lengths
pieces, which
are.
I know exact
But if I
values
make
for.
it a
Namely,
particular length, then it'll make all of the math
45 and 30.
easier. It doesn't
Okay,
compromise.
and then I can get some stuff out of this using these identities I'm about to show you.
gonna make
But
it
that's not
one.
the main point.
Okay.
The main place where this is going is calculus. You're like, what? We haven't looked at that. We haven't touched it. We haven't breathed on it at all. We're getting there. Okay, we're trying to build the pieces, right? We're going to climb a very tall tower, but you've got to start with the foundations. We have alpha and beta, which are two arbitrary angles. I can change the size. I'm going to give you 2 minutes now to work out what is the size of every other angle in this picture. There aren't that many. So you're asking, and they're just triangles. So
Better to 10.
Triangle,
for instance.
straight line,
So that's 10.
2 minutes just to work out what they are. There aren't that many. Give it a go.
Okay, now in this case, right,
I haven't broken up.
you know what alpha and beta are?
10 into 2 different pieces. It's still one tan
Won't take you long,
function.
give it a shot.
Okay, and it's just that 210 is equal to 180 plus 30. Okay, but the arguments we made for why this is therefore equal to this is an argument that comes from the graph, right? It's because tan is periodic. Every 180 degrees, it's going to repeat and repeat and repeat. So that's why that's equal.
10 180 is 0, so then technically it is 10 180.
So what you've come up with is kind of like a coincidence, right? Like I can come up with coincidences where it's like, oh, it'll work, but that doesn't mean it always works. Okay, in fact, it almost never does.
Yeah.
All right, so we're going to use this triangle. I could draw for you hundreds of triangles. In fact, there's hundreds of proofs for what this is equal to. Okay, but I like this one because it's relatively simple. I've called this A and I've called that B because I'm going to put some angles on here, alpha and beta. I'll match up alpha with the A and beta over. I think it's here with the B. Let me just double check I put it in the right place. Yes, good. Okay. Now, I've got alpha here, beta here. I need one length because I can do everything I'm about to do without knowing what any of these lengths are. But if I make it a particular length, then it'll make all of the maths easier and doesn't compromise the proof. So I'm just going to make this length here.
If you all have the simplest one,
I'm going to make it 1 unit.
Actually, no,
Okay.
all you're finding is angles.
Question.
Right?
Just finding angles. You're not finding sides. We'll get to sides in a minute. You should get exactly the same thing as everyone else. So, what do we got here?
We'll get to the sides.
We have alpha and beta, which are two arbitrary angles. I can change the sizes of these things. Okay. I'm going to give you 2 minutes now to work out what is the size of every other angle in this picture. There aren't that many, right? And they're just triangles, so you can use like angles, sum of a triangle, angles on a straight line, etc. I'll give you 2 minutes just to work out what they are. There aren't that many. Give it a go.
Relative to
Okay, that sounds like we've got some answers. Sounds like the sound of people who have answers. Okay, we'll start with the easy ones. APQ, size? 90 degrees, thank you. Angles on a straight line. Same triangle. AQP, size? 90 minus alpha. I should say 9 degrees minus alpha, but you know what I mean. Okay. Next angle, how about BQP?
Is it alpha plus beta?
BQP.
Minus beta?
90 minus beta.
Yeah. I meant the other one.
And that leaves us with this guy over here,
Alpha plus
which by angles of a straight line is alpha plus beta.
And the other one.
I'm missing, there's this one up here.
That's 90 minus alpha plus beta.
Depending on the way you write it, whether you have brackets or not, I'll write it without because I'm a bit lazy. Yeah, there you go. Happy? Okay. So we'll need almost all of these angles, almost, okay? Now I want to transition from angles to sides because that's what the trig ratios are about, right? Relating sides and angles together. So I'm going to look in turn at these 4 triangles because they're all right angled. And I'm going to look at the angles in them and what they can tell me, okay? So for instance, have a look at this one in the middle, BPQ. BPQ, can you see that, right? Now, I've got 1 as this side over here. That's the hypotenuse, isn't it? Okay? So in that triangle, that middle triangle, what is cos beta equal to? Cos beta, adjacent on hypotenuse. Adjacent over hypotenuse, right? So it's BP on 1. Do you agree with that? So I'm just going to write that as BP. Yeah? It's BP. So this is kind of funny. I was looking to get a ratio, but because, and you see why I made this 1, right? Now I find that this side is just equal to cos beta. Right? That side's equal to cos beta. So I'm going to write that in. BP, it's over here. Cos beta. Okay, so far so good. Okay, what else can you see in that same triangle? What else do you see in that triangle? I can do the other side, can't I? It's the opposite
On hypotenuse.
on hypotenuse. I'm going to use sine, right? So I'll say sine beta equals PQ on 1, which is just PQ. Okay? So I have cos beta up in the top. Now I have sine beta. Yeah, it's kind of handy. Alright, what other things can I see? Let's go to this next triangle in the corner. This one over here. BCQ. BCQ, can you see that? Right? The angle I'm most interested in is this one down here, right? Because it's going to get me to, I rubbed it off, it's going to get me to sine of alpha plus beta, right? Now this also has a hypotenuse that's equal to 1, okay? So I'm going to write out sine of alpha plus beta. What's it equal to? Which two sides am I comparing?
BC.
BC on BQ, which is 1. So that's just BC. You okay with that?
Yes.
Alright. Sine alpha plus beta. Okay. We're almost there. We almost have all the pieces. Okay. Now I'm going to have a look at this triangle over here. It's a bit more messy than the rest because we don't have the same amount of information about this triangle that we do about the others. Because there's no hypotenuse of 1 in this triangle. In fact, I don't know what the hypotenuse is equal to, so it's not very useful. Okay.
Wait, so
Yep.
if you just wrote in the one there, why can't you write it in someone else?
Okay, I can write it in wherever I want, but I can't write it everywhere, right? Because if I make one here, I don't know there are other isosceles triangles happening here, right? They're angles of arbitrary size, right? So if this is 1, I don't know anything else about the other sides, right? But I can make one of them 1, and then any other triangle where it's 2 or 3 or 4 will just be similar to this triangle, okay? Alright, so I'm going to look in this triangle here, APQ. Okay. Now what I'm particularly after is a relationship between this side and this side over here, AP and PQ. So what ratio should I invoke if I want to relate AP and PQ? I should go tan, right? Because I've got alpha over here, so it'll be opposite on adjacent. You happy with that? So I'll write tan alpha equals opposite, which is sine beta, over adjacent, which is AP, and I don't know what AP is, right? That's the whole point of me doing this, okay? So now, from that equation there, I can swap these two, right? I can swap them around. I'll get an AP equals sine beta. Now, I can write this a couple of different ways. I could write this as, like when I take it over the other side, it's going to become cot, right? But for reasons that become clear in about 2 minutes, it's not all that much of a benefit to write it as cot, so I'm just going to write it as divided by tan. Okay. Now keep in mind, these are two different angles. There's no cancelling that can happen here, right? One's beta, one's alpha. They have nothing to do with each other as far as I know. Okay. For now. Okay, so actually it's going to stay that way. They are going to remain arbitrary. I'm just going to put that length there, AP, over here. So I've got sine beta on tan alpha. Okay. Right, we're almost there. Now we're going to look at the big triangle that you wrote in the beginning, okay? The big triangle here, I've got alpha over here. I've got 90 minus alpha over here, right? Can you see that's 90 minus alpha? Because the betas and the minus beta cancel, okay? But being that I've got this side and this side, right, I'm going to go down to this angle over here rather than add in any other identities. And I'm just going to say sine alpha. Sine alpha. Okay, what's it equal to in that big triangle? Okay, and now you can start to see some of the benefits of having to say what triangle I'm in, because opposite and hypotenuse mean completely different things in different triangles.
AC.
Okay, so hold on.
AC.
Sine is opposite on hypotenuse, right? So opposite over here
Oh, sine A plus B
on
over sine.
hypotenuse, right? So I'm going to have
That's long.
sine of alpha plus beta, right? Divided by, now this is going to be kind of big because I have the hypotenuse in 2 pieces. Can you see that? I got one piece here and the other piece there. But I want the whole thing. I want the whole hypotenuse. Okay? So I've got a cos beta there plus sine beta on tan alpha. Okay. Now this looks like a mess, but it is so very close to what we want. All I want is to make this the subject. See that? That's what I'm after. Okay. So I'll just take this gross looking denominator and multiply it over. At the same time, because it's not that big a deal, I'm gonna switch sides. Okay, so I have this on the left hand side. Are you ready? I'll have sine alpha plus beta over here. Right? Okay, now step through this with me. This times this. Not much you can do with that, can you? Sine alpha, cos beta. Okay, alright? So far so good? Now what happens when you multiply this by this guy? Okay, now just to make it really clear, I'm gonna write it out. Okay? I'm gonna sine alpha sine beta, that's all fine, right? And then I need to divide by tan alpha. What is tan alpha? It's sine on cos, isn't it? Yep. So I can multiply by flipping it, right? But I don't really need to do that. I'm just going to cancel those guys, right? And then this will become times cos alpha. Sine alpha cos beta plus, we tend to write them in order of the angles. Cos alpha, sine beta. Done. And that there, just to emphasize it, right? These two sides of the equation, whatever alpha and beta you have, these are always equal to each other, whatever values there are.
So with the 3 lines, right?
Yeah, that's right. Okay? Just like a congruent statement, it's like these are exactly the same in every regard. It's just another way of writing the same thing. So this guy here, isn't it beautiful? Has a sort of nice kind of symmetry to it. Sine of alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. And like I said, we do tend to put it in order of angles. You can write them in any order you like, but I'm going to highly encourage you to always write it in the same order, whatever order you end up using. And it's probably easiest if you use the same order that I use, so you don't muddle up what you've got. Okay? As you'll see in a second, this is number 1 out of 6. Right? When we learn 2, 3, 4, 5, and 6, right, particularly the next 3, when you first look at them, they look fiendishly similar, and it's very easy to confuse them with each other. So do yourself a favor and write the identities out one way and only one way. Does that make sense?